Travis Porter. I've been with the company about 16 years. Currently, I'm working in the sales department as an inside sales account manager. My past experiences, basically about the past 10 years, I've been in a service technical support role, which varied from just a team member to the manager of the technical support. I've also had, pretty much since 1999, I've been involved with the manufacturing side of the business. Again, my contact information is down there. Feel free to contact me or any of the other guys on the sales team, and we can get you taken care of. So to prevent any more delays, let's get rolling with the seminar. Here, if I can get. Oops. Hey, guys, Steve. We've got. All right. So basically the agenda, we're going to go over some 3 common methods of calibration techniques. One is an electronics calibration with a simulator. We're also going to do an electronics answer calibration in a Drywell. And then we're also going to touch on an electronics and sensor in a Drywell with a reference thermometer system. We're going to touch on what they call component versus system calibration. So these are a few different methods of individual uses versus systems. So we're going to touch on these hopefully and give you guys some good insight. When you're doing a calibration comparison, I guess there's a few different methods. So basically in the slide, we're looking at temperature simulation versus using a heat source. So in the simulator side, you're basically only checking the electronics of the readout piece that you're using. When you're using a simulator, there are some advantages in that you get really quick responses. You're just programming, the temperature or the resistance, and then hit and go, and you're basically taking a reading. Usually on the simulators too, they're multifunction, so you can simulate either a temperature or a resistance or a millivoltage, things like that. Going kind of to the other end of the spectrum here, where you're actually using a heat source and you've got the sensor and the electronics put together, there are some things to consider that kind of limit the speed. Basically, you've got to wait for the stabilization time, heat, cool down of the heat source. So not maybe minutes or maybe possibly hours to do the testing versus a simulation where you are doing it almost instantaneously once you program the unit and tell it to simulate. And to the temperature side too, with the heat source, you're only looking at a heat source. So again, there's some things are there as far as the electronics side. So again, the big thing that the takeaway here down there in that yellow box is that when you're simulating, you're really not getting a good view of the entire picture, which is sensor piece. And sometimes, depending upon what you're doing, that sensor error can account for up to 75% of the error in the system. All right. Example, we're basically going to kind of run down a thermocalibration using the simulator. In this scenario, basically we're looking to calibrate testings 2 points of an RTD handheld thermometer at 0 and 100 C basically. What we're looking to do here in this scenario is after the calibration, we'd like to get in an accuracy of plus minus 2.2 C with the system, and we're trying to get the unit to be traceable to NIST or National Measurement Institute. So those are kind of the criteria that we're trying to accomplish in this scenario. So we'll just kind of run through that, and then we'll kind of go over the what we may or may not have done properly. Are new. Usually the readout pieces are calibrated to a DIN curve or intended to be used with specific TCs. When I say a DIN curve, that's referring to an RTD, usually the IEC DIN class A or B type. So again, typically that's just a defined 100 ohm platinum RTD with either class A or class B specification. And that's kind of what we're looking at here. Our readout has a resolution of 0.1 degrees C and it's supposed to be accurate to 0.2 degrees C. Basically, the adjustment. In this scenario, the unit or the readout piece has a trim pot 1 and 2. Basically, that's a 0 and a high trim pot that we're going to be looking at to adjust. So in this picture, it's kind of showing what we're going to be doing here. So the rough drawing here, but in this scenario, basically we disconnected the probe portion or the sensor piece from the readout piece, and now we plugged in the simulator. In this scenario here, we're actually got it connected and we're simulating 0, and now we're making well, we're not going to make the adjustment yet, but the screwdriver represents the trim pot 1 where you would make the adjustment. A little more technical difficulty, so I can't get to the next slide. All right. Let's make sure. All right. To calculate the electronics of these temperature systems, it takes basically an input or an out, and then simulates an output. So in that scenario where we're looking at a 0 and a 0, we're basically simulating temperature. Most of these handhelds that you see on the right here can simulate both millivoltages, resistances, and temperatures. Or if you type in, I need to simulate a thermocouple at 100 degrees C that's a type K, it'll output or simulate the appropriate corresponding millivolt. And also true with the RTDs. In this scenario, the first one we were kind of showing 0. This one is it's similar, but we're down on the flip side of the 100 degrees C. So again, we've removed the probe piece, whether it be an RTD, thermocouple. Folks will even just simulate resistance if they're using resistor measurements. But basically, we're now the simulator to the thermometer. We're going to have a good connection, and then we're going to simulate the temperature desired. Typically at this point, not to jump too far ahead of ourselves, but this is kind of the first piece in kind of recording your as found data. So here, as far as calibrating with the simulator, so again, whether you have a thermocouple, an RTD, or you're checking just resistance, basically you're going to disconnect whatever the source is from the readout piece and then connect. For our example, where the 0 and 1, we're going to near 0 C, which relate to about as far as an RTD. So again, we'll manually record the. So next step is a simulate C, or roughly a system is going to be about 8 ohms. Record that data. However, as found data, because this is going to have ability, if a customer knows the performance, it's kind of key information in case you're traceability, seeing if you were in for left from. So today we're basically going to set the simulator, or again, and at this point, this is where we're adjustment to the trim pot 1 or the low, and then we're going to process or 100 point. Maybe after done that, you'll want to go back and I've seen upon how good the slopes. I may have to hedge a little bit since dealing. See, in this example, we'll keep them. I have to go up, say, a 0.5 and then 100 slope. So again, you make a compensation is near, and you may have to go slightly or 0, but to get that 100 down. Example I was pointing across. If you dial and you go back and check your at say 1. So now your 0 is dead up end of the span. You're a little bit have to take your 0 down and pull that 100 C point, pick your 0 up a little to make 100. If it was say 7 up slightly to get it closer to that point for. And muddle that too much. Scenario, I guess, is and things to we'll kind of go back in the Q&A. In this method, could the calibrate that we did be considered in this trace? That's one thing to consider. If to true or possible, those sort of steps must be taken made with the R to be traceable. So, I don't know if we jump, but talk to these for a moment. Is this considered traceable system? I would say no. The system electronics that probably is dependent upon your simulator. In the scenario, the simulator already has a traceable calibration. So basically, when we're saying traceable, we're proving basically an unbroken chain that can be taken all the way back to NIST. In this example, we broke our unit under test basically and are only simulating half the system. So in order to make it a completely true NIST traceable, we would have had to include that probe somehow. So to kind of address that third bullet point, what would we need to do to make the entire system traceable is that to include the probe. And so as we move forward here, we'll talk more about including those or that last bullet point. So again, the pros of calibrating with a simulator, obviously it's very fast. Settings and the readings fairly instantaneous. There's not a whole lot of stabilization time. But the only considerations is your ambient. So if you're in a room extremely hot or extremely cold, there might be some considerations around that basic unit specifications. Most of the time, these simulators are fairly portable. Even larger ones you can use with this one hand. The other thing that simulators is use sometimes probes, or you can different types of RTDs, and kind of touched on to be considered is that probe here was kind of taken out of the process on the electrical that piece and calibrated. Therefore, that the argument system, once you put it back together, possible. So, going to get a different comparison calculation using and actually simulating. Something in this one, you'll notice that we're breaking this really. So again, hit out and our probe, we're showing making an adjustment with simulator. So in this, our the source for the temperature. Consider if we were to go in specification 2 before of a 0.2, the Drywell, excuse me, display achieve that. Typically in the industry, folks will 2-to-1, or if you've even seen on the application as well as a 1-to-1, it kind of comes around to buddy think in the process that it's being used in. So again, across the little picture, basically we've set our to 0, and now we'll display accuracy of this case where we want to see within the 0.2, and have plus or minus 0.100 now achieved what we are looking to do, system calibration. So quick steps here to what we did in as process. So Drywell, where desired test point case would be 0. We're going to wait for the unit and then stabilize and to record that. And then again, we're going to move second test point, which was 100C. The Drywell will take 100 and take our point in the process. So again, here, this is keeping its foundation, has a lot to do with reverse and going back if there is a problem identified. Once you've got in with we're going to go back and reset the Drywell, and this time we're stabilizing, this time make the point to within the tolerance. Want to see on the readout, move up to that C point and adjust to your adjustment and do a read times. You may get either slope a little bit on either the fit within the tolerance that you're after. So again, there used to be a unit calibrate here and have to at 0 where we want to set 0.2, but with a 0.0, and then at the top end somewhere close to 7 or right. And I think a bit of a internet making flashes if you guys experience a little internet here. Hear me? I'm getting a little loose. Just again, computables this morning when we're setting up. Okay, Steve is back control the computer. Can you hear me? And good, and he's gonna. Okay. All right. That's so to recap. Questions. Now, could that be considered a calibration? And then the second kicker there is so what have to be true to make. And again, too, there's kind of a warning. They might need a little more information. This scenario, it's be considered traceable. It's kind of a yes/no thing there about the piece of information is your heat as the reference rated to NIST, or can you prove trace that piece? So that's the warning. That if your heat source has a NIST traceable calibration, the source calibration, yes, it would be NIST, because now you can chain of I went traceable unit to my unit, so now I can prove sharing of traceability. All right, in this system. Pros and add a system. The other one that actually uses simulating electronics, there are some that can be versus users. In this case, we probe and the readout in temperature the world to be using that in the problem. The other thing, very simple to set up, and we just use does it get us 104. Some cons maybe is going to be limited by of the other piece I will. If you're coming up with what is getting very tight, most drywell view that maybe you're looking for, you have to go with a 2-to-1, or even it's all kind of on the unit that you're testing what the capability is of the drywell. Or something to consider is when using a drywell, most of the specs are
okay. I think we lost Travis's audio. Let's hold on. We'll try to get him back.
All right. Apologize on that again. If you can, if you can hear. Gotta turn our do this again. All right. So another thing to consider, well, as most specs are basically, if you're using short and not reaching the drywell, that's something most control sensors where you're coming from, since in the bottom up unit. So what you're trying to tip of your sensor with the kernel. You want to consider when basically is usually these are then married. Basically, you've basically prevented by through the electronics of the basically compensated potential errors or probe. Any other thing, temperatures that you're dealing with for the drywell temperatures could take especially if you're taking it may take move between these data points. Next one to touch on, same technique, but further in that we're also here an external reader. So when we're reading to the display, we're going to actually use it, which is going to increase in this type, the external reference by several magnitudes by just the display of the drywall. So if the drywall is a 2 dimensional reference, that same range that you're going to get an uncertain reference in Pro 0.025, 10 times better with the drywell. So again, the decrease, I should say, increase your accuracy, increase your uncertain. One thing to note in the touched on kind of the last slide is the red and the drywell. So that's trying to complicate situation, trying to get all immersed at the same. Basically, their real resource or the heat in the heat source. Not on the slides is something to make sure you go out to the top. You're going to your made. So again, cold unit, you're going to see the temperature the closer you or further away you get from being fully immersed in the unit there. All right, so again, back to the stat, similar again to the other 3. So in this one, it really changes. We now added an external to improve upon our uncertain or accuracy that we're going to be referencing to. So now, what is the thermometer. So again, in the application, we're going first to 0. Unit test in there, let it stabilize, take our as found. Again, it's always critical to get that as found data in case they are paying for this, they don't have in-house testing. Go back and kind of do that reverse traceability to see if they've had compromises in their QA or processes. As found data, I'm going to move a data point here, which we want. We can let the here as found data, and we're going to again of the moving 3 computers I'm jumping to. I'm going to take the as found data, and then we're going to record to the adjustment phase of where you're going to adjust the pot 1 and 2. First, that I'm going to touch on now versus he says once you got you're already at the 100 point, could the pot 2? Yes, that's probably an acceptable method. Save you some time in that, and then made an adjustment after you've you go back to your 0 point and make there as well. But again, too, you would always at 100 point to make sure your adjustment some sort of a slope or hysteresis that's going to throw out. So again, that's why it's always good to call them in, and you think you're back and get some as left data with the unit, those points. Pros and cons with this one, you're basically going to get the best accuracy results, and that's simply due to the fact that we're using an external reference probe and readout, a magnitude better than what you're going to be a reference or heat source display. Typically with a readout and ref pieces are the calibration that you're performing will, again, it takes out of the equation as a factor other than just simply being a heat source. Again, in this regarding versatility reference, you can get different probes that are different shapes inside, kind of more what you may have in your whatever the unit that you're testing. So again, you can kind of get a real world with quarter-inch diameters or 1/8-inch reference probes that have these same better read on how they're actually performing in the environment as test. The cons here or these more equipment, so cost. Again, you're using a readout and a ref source, so again, more involved in the setup. Same bullet point here, system calibration, the unit's individual typically. Now you've compensated for both the error of the potential error of the probe with a single calibration. Time is a factor here as far as moves and repeating the temperature things. We had ranges. Sometimes I think that something to consider, but right now there's not a lot. We're really limited as far as range. We can get anywhere from about -200 up to C, and you can use this comparison techniques and a good heat sources that are spanning about so about 1400 degrees here. We're going to kind of jump kind of a system calibration. So examples that we moved through was kind of one-upping the techniques of calibration. Now move towards breaking them and moving to the individual pieces, kind of paying more piece or component of these. And in calibration, the probe is calibrated in a conventional manner. An RTD situation, again class A or B in the world, is TS90. You'll also hear about CD, or these are all methods behind how the probe behaves or its resistance curve versus temperature span that you're calibrating it. And the readout piece is actually also individually in a conventional manner get to a known stir, or you're simulating to a very high voltage in the piece. In this type of calibration, individual trace the probe under the traceable, you readout piece, and then when they're both have their you've got now a completely traceable, but each piece's performance or what it may be contributing. So the differences there between the system, and the piece can be broken out. They're married, so once you cal them in a system, you can't interchange them. We're comparing them to a reference thermometer. Calibrations aren't performed, and the traceability applies to individual pieces, which component. So the big thing to take away from where you're looking at the probe and the readout versus calibration is that the system calibration, any error that's contributed by the probe will be compensated through the out piece. So that's one thing there. All right. Component calibration, I'm advocate of them based on the product side, because it versatility in having each piece have characteristics. You can use that in piece with different readouts, and so that's why I'm advocate of that. And then he's with these, because again you're looking at each piece versus a system where you don't know where the it was contributed by the probe, or who knows, we've just held it in with the error. Actually taking a very hard look, the probe's persistence versus temperature, and then math. And with the readout piece, we're actually applying of a known resistance per millivolt. So again, be straightforward there. In the station certificates, you're going to see certainty provided for, or in the case of the readout known, or what was applied, what was read, and the error, again, very straightforward. And it allows you that versatility to have the people. So if you have multiple probes in a single room, it gives you some flexibility that way. A little bit more expensive, but again, you gain, that's kind of a weight argument, I guess, because if you have and multiple probes, it gives you versatility with capacity for your processes. Things that are with the component calibration is not in temperature units, so typically get a millivolt or resistance, and then on the probe side, resistance versus temperature. A lot of folks don't like this. It's a little bit harder to explain to how they play when you're using them together. The component or a formula on your readout accuracy and the uncertainty of that. So again, there's some conversions or math that you should be familiar with to kind of help ease an auditing process. It's not always acceptable by audit. Had anybody run up again issue with our certs where it's just accepted? Again, it's being able to the way the calibration was done and how again going back to the system easier, because it's basically the system read the tolerance of the reference, and here's your error, and much easier that way. For a difficulty around it with auditors, we do offer not some calibrations, but so basically we do take the integrations and apply those, but then for the DW testing in their process, we will plug the units back to some system data. We're not making any okay, we did the individual component calibration, the pieces together, and to present to an auditor. So it usually is help ease that. Okay, pros and cons of a system calibration. I apologize if I'm not keep lines, but they kind of iteration. It's kind of how you toss us. So some of the pros, they tend to, because again you're getting individual pieces. Then temperature units. Typically, again, we're going to show you what our reference is reading, what the error is, to really interpret versus you may be saying, okay, I have a 20 part per million out, and I'm looking at 0 degrees. How do I make that work? So again, the results are the temperature units. It's in an auditing situation why we offer these, and that's mainly for folks that want the robustability of component calibrations, but also wants their auditors. Again, we've touched on a few times here. Sometimes the uncertainties can be difficult. So again, system calibration and the unit is 2 degrees C. I don't know if the 0.2 is coming or the readout or a little bit of both. Again, there's that in aspect. They do lack a little bit of robustness in that again, too, with the components are typical. Again, that's due to the compensation and readout error are being all adjusted in a single, the electronics in the. So again, to think about there as far as what's for you. I've seen a lot of questions coming through. Steve is going to chair up some of these, and we're going to, as quick as we can, and hit as many as we can. Hopefully, I don't know what the time is, the clock. We'll get to as many of these as we can.
Okay, I think Senator Travis is going to switch over there, and then I can questions, and here's here. So let's get these. So we've already got quite a few questions. We'll go through those now. If you have additional ones, please text those into me, and we'll get started answering these. Let me go up to the top here. Okay. Travis, connection wires during simulation, K or typos.
That I believe is, so there are different.
Hold on. You're not on. Just
can you guys hear me now?
Get that now.
That's better. Seem to have gone deaf on my side.
Try it now. Go ahead.
Test.
Yeah, you're
back. Okay, so it looks like we've got a little lag in the internet here because I'm getting a pretty good echo. So depending upon what you're simulating, I think the answer can be yes and no. If you're using a type, and I think this applies more to base metal, and that's not something I've had a whole lot of experience. Usually in those scenarios, my understanding is the appropriate type connect. Otherwise, you're basically going to create a new thermal where you're making the connection. The flip side of that, a lot of folks will just use the pure copper to copper for the readings.
You want to mute yourself. Okay, next question is simulator as a standard acceptable specifications.
That's kind of a loaded question. So with a simulator, basically it's like with anything else. There's usually several levels of accuracy that you can depending upon range and accuracy requirements would kind of be what grader that you're going to purchase. So it may not be as a multi-function, which is definitely not going to be up in these processes. We're used to the bigger box calibrators. Certainly as far as PPM goes, maybe from 100 parts to 20 to 5. Again, it just depends on the actual sim you offer them, and as far as what they're capable and as far as what they're regarding the actually range.
Okay, the next question is, you talked about traceability. Did you mean traceability to SI, or is it to the SI through NIST?
I think it was the SI through NIST. So again, basically in this representation, we're trying to prove our testing can be then shown to go back through an unbroken chain. So again here, the units under test are basically the reference. So final system calibration, let's say a heat source that has its own NIST and a reference probe and readout that NIST calibration, that the unit or test could then be traced all the way back in that.
All right, the next question is about your sensors. Which ones are the most accurate? So you talked about thermocouples, thermistors, RTDs. Maybe you could just spend a minute on that. Okay, so that's,
again, there's a lot out there as far as what you can get as far as accuracy. And again, most of it is based around range. If you're looking at a fairly small temperature, 0 to 100 C, actually a thermistor pull about is probably your best regarding accuracy. Over that temperature range will net you approximately any 0.01 to 0.006 in that sense. From there, you kind of have to go with the trade-offs. If you need more range, the next jump you can make is, and you're going to lose some versus the thermistor over that range, gain temperature range. Next kind of move that you can go RTD, and again, there's various level classes all the way up to how we with a very specific I-find coefficient. There's also calendar values to interpret the probe's resistance to temperature. Again, then moving on from there, more range and more accuracy, you move what they call an SPRT or standard thermometer, which is a different way they build the sensor, typically what they call a strain-free. So again, accuracy, but again, too, working with that level of some additional pieces regarding a water cell to kind of plot your drift and different things, or you can not be done. But usually at a bare SPRTs, you've got to have the side to that couples. If you've got a lot of room temperature and you don't need a whole lot of apples are the way to go as a plus minus 1 degree C. They do vary roughly off of that, but again, that's where I kind of, but again, too, even amongst the thermal, the noble metals of them, which are the BM, which are the type R and type S, where we a fixed point calibration to perform fairly actually old temperature range typically was from about 0 to over fixed point. So it's roughly about 1,000, and then we extrapolate the data up to 1450 C. Again, as far as thermocouple goes, they're going to give you this temperature range, but you're going to lose the PRTs are kind of depending on which side of the scale, it's more of an industrial PRT, or reference PRT, or SPRT. And then again, absolute narrow temperature range, but really good accuracy. Thermistor is
the next
a great way to go.
What depth did you insert the sensor into the
That's a really great question. Rule of thumb that's taught to me on immersion depth to help negate any stem conduction errors. You want to go diameter of the probe or the length of the sensor. So that plus typically applies to RTDs, and I've done those to usually assume sensor of an RTD is the act length may vary, much up to 1.5 inches. Getting that information from the kind of the plus rule of thumb, we'll hedge down and do 15 times the diameter. Again, in the business edge on the side, 20 times the diameter plus the. So roughly, if you have a 1/4 inch probe, 5 times 20 plus 1, you're going to have 1.5 to 6 inches on minimum immersion depth.
Okay, the next question. You talk about using a Drywell calibration, that there's an internal sensor in the Drywell that's mapped to the readout there and the reference. Could you just talk about the accuracy
so
of each one of those?
The sensors that are used in the heat sources are typically an RTD. They may be in class A or something. Those type of accuracy, the readout or reference. So again, the heat source typically, you can accuracies are in the tenths. Sometimes we're able to achieve a digit like a 0.02. Or the reason you move outside of reference thermometer is simply and it's just going back to the grade of sense in the actual component. Where we're not absolute accurate. I'm not going to use like a or SPRT grade sensor. There's some too with cycling up, cooling down that you're going to see maybe some history that it's going to be hard to compensate for. So the spec of the heat source tends to be wider, higher during reference. So it's basically we're the internal component, so we're not using a measurement circuit versus a emitter, which has its own built-in reference that we're referring to help interpolate the. So again, it's just coming down to a difference. And if you were to do some research on a whole lot of different keys out there, they're classified, again, anywhere from the DIN-B to PT100, so that wine sensors, and then they use defining them. So they may be, if it doesn't meet class A or B requirements, them using a calendar Van Dusen or ITS 90 calculation for that temperature. So again, Jack, and recap, we're basically a reference grade RTD sensor for the control sensor in the heat source.
Next question is, can a Drywell be calibrated, and how would you do that?
Yes, the Drywells can be calibrated, and in the one example, if we're saying the Drywell is traceable, it would have to be calibrated. And the calibration method would actually almost refer to that slide we went through where we had the unit in the heat source. The only component you would be the unit under test would become the unit under test. Upon the Drywell's range and accuracy capability, some of them have a they're a controller that's used in the unit, and so some very simple to having like a 0 and a span off adjust and get that slope correct. Some had an RO alpha delta or a calibration spec to basically was defining that in terms of nothing more than an RTD curve of the Drywell. And 2, as we move advanced Drywells like we saw, so go from a metrology well, now you're dealing with a rate of adjustments in that we spec for EO gradients, different things like that. So the calibration process becomes a little bit more involved.
Are there units for Drywells where you can accommodate more than, say, 3 to 4 UUTs, or if you calibrate thicker sensors?
So depending on the drywell and its capability, there's something you want to be aware of is loading effect. So basically, if you have a well, you're going to put a hole, you may have some loading error. Have to watch for. We also do count the inserts. I was actually working with where he had a sensor that was 3/4. So the challenge there was matching him up to a unit or a drywell. He had enough capacity to induce and control test that sensor without it or causing a loading effect on the drywell. So again, yeah, we do have options there. We also have drill things, and you can call and speak with one of us on your application, get us some specs. We can kind of make it if a drywell fit with a good design. Now there are this where there may not just be a good. You may have a very short, wide sensor, little steam plug sensors that I've dealt with. To test those, we have to usually end up going to just simply to get good conductivity, heat source, or a drywell as far as getting a good thermal conductivity and results to the display.
The next question is related to inserts as well. So for higher applications, like when you're up 1500 degrees Celsius, what types of
for ours,
material would be
so
used
again,
in those
lower
inserts?
temp units, we typically use aluminum material, and then as we start moving up, it's like an aluminum bronze, a yellow bronze. The highest metal insert we offer is about, I think is what we take it to. It's kind of a mix of an aluminum. Above that, all the inserts in our products are made from alumina. That said, there are folks out there that different metals at those applications. So a lot of folks will use ink now. Used a lot. The dent is very hard and it's very difficult to machine. So again, for our applications above C, we typically move to a aluminum. So again, don't confuse that with aluminum. It's alumina, and it is a high temp ceramic.
Okay, the question is has to do with interpreting ISO 17025 calibrated standards in terms of temperature and certainty. Can you comment how you do that?
So I guess what are we interpreting as far as uncertainty? So typically, whatever the piece of calibration. So I'll just go of what we do in-house. So it's a PRT probe, a series of baths, a reference readout, and a reference. So each component, reference readout and bath is going to compare in that measurement of what we can do with it. So we've gone through dedicated baths dedicated to a specific, these are ITS 90 temperature, gone through and done a very robust where we include the uncertainty of the reference probe, I guess it wouldn't be the uncertainty of the bath, but it's bath, and then there's some other pieces, an uncertainty piece that kind of plays in with your U. You kind of crunch those numbers, the overall uncertainty that we say our calibration process using a comparison method bath at this temperature, we have an uncertainty, and that's how we go about kind of breaking it down.
All right, the next question is, do you typically check intermediate linearity points of, say, 25 and 75 degree of range after the
yes, and in the slides where we kept it short to the 2-point cal, it's actually very good to have interim points between this testing. So again, in our slides, to shorten to the point 0 and 100 were the points in question. You testing in between 550, 75, it would be those where it says when you make the 0 adjustments to go back and double check. You can always check them on the way back up, and again, that gives just adds a layer of robust to your calibration.
Related to calibrating thermocouples, and a question about how, as far as the reference junction in there, maybe you could just talk a little bit about calibrating thermocouples and reference.
It's a little tougher to talk to because they don't have a whole lot of experience. Because in our lab, we typically only deal with the RNS thermocouple. Reference junction, to my understanding, this reading a thermocouple, what they refer to as internal reference junction. So if you have a readout and the internal reference is, or JC, is set to internal, means as part of the measurement, the way it's been explained to me, there's something temperature that measurements to compensate what it's and actually drop it like it's seeing at. So basically, I've been told actually measuring the thermocouple is 0, so you're trying to measure that, and since an external cold junction compensation at 0, they build into it. And that's one internal on the readout. For our process, when we rate them here, we actually attach a cold junction. So we, at the point of thermocouple exits, so the two opposing metals are, we connect there, and we drive that in. And then from there, we the copper. So basically, we're getting a true millivolt reading from whatever the thermocouple at 0, and it basically helps differential of your uncertainty by dropping the point. So again, your volt reading in your thermocouple calibration. Our text to it. So again, our thermal test will be in a fixed point cell, say at 660 degrees. Fires will come out, and they'll go into a basically, and then we're taking the reading or millivolt at that point out, in a real differential between the temperature the thermocouple is at and 0.
Can you talk a little bit about how you would present the results of calibration in a report?
Usually in a report of test, as we talk to you, you're definitely going to list, this is kind of quick, but you're going to want to list all the pieces that that'd be your heat source or your reference thermometer if that's a piece. 2, you're going to want to have typically a known uncertainty to run some numbers and say in this process this level of uncertainty uses a reference equipment. From there, it's recalibration situation to found data for your adjustments, and then you're going to report all data. So again, if you look at most calibration on a recalibration type situation, a set of data that says as you sometimes can see in or out of tolerance, and are made, and then there's another that mirrors the incoming data, the as levels. If we were to create a calibration run, we would show the as found or 100, and we're the 0.2 uncertainty. We would have to have a statement of, these at 0.2 uncertainty, and then we would have unit under test, and then what the tested as left
next question is there a Drywell that's adequate for radiation thermometry use?
Not a Drywell, but we do have some IR calibrators, which would, I would think, be more in line with that without actually knowing what the radiation thermometry. It would kind of be hard to talk to, but we do have a series of black bodies that are intended for more of the radiation or IM, and we do a true reading on those. So again, pending what you're with it may or may not be a good fit, so we would need a little more information there.
Can you just talk a little bit about the traceability for international standards when you're using temperature?
Traceability for international standards. So again, I guess I don't want to take this question. Every country that participates usually, so every country you're in, typically referencing, so in the East, there's different labs all over, and China has their own lab, various labs all over, and for that country, standard or what defines what temperature is. Bigger worldwide spec where you conferences, the people that are involved in metrology from around, they kind of agree to what is temperature. Here, I think there's a term called agreement where it's like various different countries and participants agreed that it's a little different than yours, well, mine's a little different, all agreed that they're all sound and we all will as being relevant. So big picture of how it's done worldwide, as locally or within country, you're adhering to the country that you're in. National lab is required.
During the presentation, you referred to 4-to-1, 2-to-1, and 1-to-1. What is 4-to-1
that is referred to your test uncertainty ratio. So in an example, if you were calibrating a readout with the thermocouple at an accuracy of plus minus, typical industry wants to testing that the uncertainty of whether it be a simulator or be 4 times better. So scenario, if we're using the heat source, have an uncertainty of 4 times better than what the unit you're testing, the plus minus 1. So you minus 0.25 on the temperature reference and heat source technique that you're doing. So again, and then the 2 pretty self-explanatory. You're going to be like 1 degree, so you want to be at point. Throughout the 4-to-1 is kind of just the standard that is used.
The next question is,
the best
after an adjustment, how do you verify whether the meter is accurate or not?
That's again going to with the as left data. So you take your as found data, you make adjustments, and now you're going to read the same temp data. So again, there in that as left, that's where you're re-verifying that the adjustment is correct, and by found data, and you're saying, okay, I'm out, so I'm going to compensate 0.2 degrees up or down, and then I'm going to go back data point and make sure, 0.2, I'm seeing 0. So again, it comes in, and I believe another person asks, are always good to take kind of piggybacks on that as far as, yes, it's always good to kind of more in calibration.
Next question is, what measurements would you need for an uncertainty budget if you're doing a Drywell calibration?
If you're actually calibrating the Drywell, it's just going to come down to your readout and your thermometer. So it's the probe and readout, basically a simple piece of what you're using to calibrate the dry. Again, too, if you're using the dry with the heat source, and that's kind of that second example we did direct to the display of the heat source, it's the reference thermometer and readout that you use. For most of us, or most of those that we calibrate, most of us around our 5628 PRT and our black stack module with a 25.
Next question. In your presentation, you mentioned curve. What do you mean by
this is a predefined curve for RTD. So basically, a lot of sensors are wound toward ohms. it's also relating to the grit in the actual sensor winding. So to have a sensor with a specific grade of platinum and then trimming the sensor, so you're going to wind this platinum roughly 100 ohms. What they have to do is trim it, so you're actually measuring this to make sure it's within 100 ohms, whatever the DIN class requirement is. That you then assume that because RTDs tend to be fair, so once you've trimmed this sensor to meet specification, its resistance should perform within the DIN class specification. I think the A or B is again platinum used in the actual winding, and the A and B is more defined. So RT is going to follow so 100 ohms at 0, and then as you go up to increase in resistance up to, I think it's to the 420 point, but it's followed. So if you were to map that, that's basically what the DIN class A and B says is in class A or B winding. You will certainty across this range, so it's kind of meant to fit for an RT resistance.
When using a Drywell for calibration, is there an issue with using an external traceable RTD as the calibration reference that has a higher accuracy?
That was in the third example
sensor
we did, where you're using the external piece with an external probe. That's one way to the overall uncertainty in your location. So again, in terms of these Drywells, depending upon the accuracy you get from them on their just terrestrial type PRT versus a higher grade reference thermometer that's going to be found in your probe.
If the temperature range is, say, 40 degrees Fahrenheit to 70, then it would be better if we just test only in those ranges?
That's yes. I mean, if you're only concerned with those, you can make your calibration very defined. If you where you like maybe outside, it kind of goes back to some robustness. Or only say at 40, 50, and C, and you only calibrate at those points in the uncertainty you need. That's perfect. Sometimes folks will go of what they're typically have to go outside the range. They're typically find the curve fit. So when you're defining out, typically there's minimum tests required to make that. So in the 60, 70 degrees C, if you do an external reference, and that's acceptable. But I would assume that if your reference that you're comparing to would probably get something a little done to it, or over a slightly wider temperature range.
Okay. Next thing is, what is the distance to be maintained between the UUT and the Drywell calibrator and the well?
Not quite following that one. As far as the distance remains, depending upon the calibrator. I mean, if you got one that's putting off some good feet, is usually what you want to. Most of them, if you're on a fairly mild, be a minus 25 C to 150, going to be outputting much. Again, just some as far as potential. Your other equipment is about the best I could recommend. When we're testing in house, we keep about 6 to 8 inches between units.
Okay. Well, this has been a particular topic. We've received a lot of questions, and unfortunately, we're probably better right now, but we've tried something that we can. Let me just wrap up here and tell you about seminars that we have coming up, a bit about system calibration. We did a seminar on how to system calibration for an RTD last month in English, and that's exciting. On March 11th, if Spanish is your native language, we'll be doing that same seminar. And then on March 25th, our Chief Corporate Metrologist Guy will be giving a presentation on Introduction to the ISO Guide Uncertainty. So if you want to know about uncertainty, that'll be a good seminar for you to mark on your calendar and attend. We do have training classes here in American Fork, and we'll be beginning our 2015 calendar of training classes here in April, and then there's some others that throughout the year. So if you're interested in getting more hands-on instructor-led training on temperature metrology, please make note of those classes. So we appreciate your attendance here and all the good questions that we received. I'll be sending out a link to the recording on Friday. And if there's a question that we didn't get answered, feel free to respond to that email back, and we'll get a response to that. So thanks again for attending. Hopefully this has been useful to you, and hope to have you join us on a future web seminar. Thank you.